Okay, so we're going to go through and do a data structure this time around. I went ahead and did some work prior to starting this video because there's a lot more going on. So what are we going to do? First we're going to do is implement a tree structure, and I'm going to try to walk you through some of the nuances in C++ and properly executing this implementation. And then we're going to go through some algorithms involved with this tree data structure to implement a breadth first search solution and a depth first search solution. Now, before you proceed, I advise you to go ahead and open up the Wikipedia article on what a tree is in computer science, so to get yourself some baseline on what this entire video is going to be about. So let's look at what we did before getting started. So I went ahead and created a structure from which we're going to work with. I created a node structure in C++ called TN, standing for tree node. And you have three publicly accessible values that will be stored in each TNet. Int for val, these nodes will maintain an integer value, and then you have pointers, LC, RC, one for left child, one for right child, and as it goes, the left child will have a value that is less than the value of the parent, and the right child will have a value that is greater than the value of the parent. And I have two constructors, one that is a default constructor where you instantiate the value of the node being created with the 0, and the other one where you pass a parameter to the constructor, and that value for the node is then given that parameter. Pretty straightforward stuff. And then I have here the pointer to my n in the test bench code under main, and we're going to go ahead and run it to verify that it is in fact written correctly, because I can sometimes be a little absent-minded. And there you go, 0. Alright, so let's go about doing this. So a tree has a couple operations, but we're just going to stick with two operations, or one operation, an insert operation. So what an insert does is it takes a value and the root of the node for that tree, and we're going to go ahead and try to place it appropriately based off of the current data in that tree. So let's look at the signature. We're going to want to pass it the pointer to our root, and then you're going to want to pass the actual value. Now we could do two things. We could generate a node and then push it into the tree, or we can generate, let's just pass a value and then have the node created within the void function. I think I'm just go ahead and put in the integer and then generate it within the actual function. Let's call this new val or nval. Alright, I want to drop that nomenclature about the underscore, and I didn't give the void the function a proper name, so let's go ahead and do that. We're going to call it void insert val. Alright, so with that said, let's go about and identify how we're going to go about inserting this. But first, let's go ahead and put a test bench here. So insert val. The first one has a 0. Let's give it another value, a middle value, right? Let's give it 10. Okay. So let's pass it two numbers, one for its left child, one for its right child. Very simple. Let's give it 5 and 15. Straightforward, right? Okay, so we're going to pass it two values. So how do we go about inserting it? What you want to do is determine if the node we're operating at is null. Then you go ahead and insert the value. So because you can't really check a null pointer for a value because it's a null pointer and it'll throw a null pointer error, what you need to do is actually kind of look ahead. So let's first start out by determining if both the leaves are null pointers, because if they are, then that means we found a leaf and we can just insert the value from there. So if LC equals null PTR and RC is equal to null PTR, we are going to find that we can just insert it. So at this point, we just need to know if it's left or right. If nval is less than root, we use the arrow nomenclature because it's a pointer. If the target value that we're going to insert is in fact less than, then it's going to be a left child. So let's do that. And actually, before we do that, let's go ahead and create the node. So new node, our end node, is going to equal new tn for nval. And then we can just assign it accordingly. So root lc is going to equal to n node, else, and then you can just return it. Else root rc is going to equal to n node. Because if it's not less than the root value, then it's clearly greater than. And actually, no, I should put another else if, because if it's equal to, we don't want to insert duplicates. So if nval we don't need the brackets technically because it's only one statement. RC is going to equal NN. Pretty straightforward. And then return. Okay, so let's review what we just wrote. If we enter a node, oh, we didn't properly access the nodes either. It's the left child of the root node. So because LC isn't by itself defined in this context. Alright, so we go in, and if both the children are null pointers, then we have an opportunity to insert a value. However, if that's not the case, then we just need to check two instances. And we're going to kind of replicate some code here, but if nval is less than root val, then we need to go down this thought process of, okay, I'm only concerned about the left half. So what could happen? The left half could be null, or the left half could not be null. So if it's null, let's just go ahead and insert it. Then just we do need bracket because we're going to do two operations here. Tn pointer and node, go new tn and val, root left child is going to equal and node, and then it's just going to return that. However, if it's not a null pointer, then we need to go through the process again of, okay, we need to go make that the current root. So let's go ahead and make a recursive call, and then we're just going to return whatever that recursive call does. So insert val, but instead of passing it root, we're going to pass it its left child, because we're looking down the left child of the path, and we can just pass it the same number. And then we're just going to do the exact same thing for the right side. So let's copy, paste, and then make some amendments to make it for the right child. So else if n value, we're doing else if steps to slay and go through because we don't want to have duplicates. So, and then if it goes through this without doing anything, then we just return. So I mean, the compiler already does that. But anyways, nval is greater than root val, then it needs to be a right child. So if the right child is in fact null, then tn new node is going to equal to a new node, assign it to RC of the current root, and then return it. Otherwise, insert val and then traverse down the right path of this current node, and then rinse, lather, repeat. So what we're going to see now is, because we don't have any traversal algorithms written, we're going to have to kind of manually call them. So after the insertions are made, we should see the root value is going to be my n val. And then the root left child is going to equal my n LC val. And then let's do the same thing for the right side. Root right child, sweet child of mine, RC, and that should be good enough to demonstrate that we have inserted values appropriately. That's a nice first step, right? Okay, so our root is at 10, our left child is 5, and the right child is 15. All right, cool. But now when we start doing multiple numbers being inserted at a larger volume, we don't want to do that manual line by line by line read out and print out of what value is from what node. So obviously we need to implement a traversal. So let's open up the file again and go from there. Now, what is the difference between DFS and BFS? So breadth first refers to the layer at which you enter the tree. So the root, if you draw a tree out going top down a piece of paper, you're going to see the root printed up first, and then the next level from left to right, and then the next level from left to right. And then the depth first refers to exactly that. You don't print until you reach the very bottom leaf, and then you print everything within that depth. So everything at the bottom, up, navigates the child to the right, and then it just keeps on writing. It just keeps on writing until when you're finally done, you should be at the root. So let's go ahead and start with the depth first. Traversal. And I'm just going to do a void because it's going to print out by itself. So void DFS, pass it the root. And that's really all you need. And this is going to be actually pretty simple. So what you want to do is first print, if you're at the root, what needs to be printed before you get printed? Because it's depth first, your children need to be printed. So call DFS root LC, because we're going to go left to right, and DFS root RC. And before we even do that, we need to do a check if they're not null. Well, actually, no, that's not good. If root equals null PTR, then just return. All right. If it's not null, then you're going to go ahead and proceed with the current root you're at. Put your children before you. And then once you get your children done, then print off what you have. So cout, let's just print out the value. All right, and then that should be, it's really that simple. Now think about it though. So in our example, where 5's at the root, or 10's at the root, 5's to the left, 15's on the right, what's going to happen is DFS is going to call the left child before we even get to the data in our current parent. So that's 5, right? So 5's going to print, and then DFS on the right is going to print. It's going to print 15, and then we're going to print our root value, which is going to be 10. So let's do that, shall we? DFS. There you go. 5, 15, 10. That is depth first, right? Now let's do breadth first. Alright, so it's kind of the same idea, except with breadth first, you're going to change the order around. You want to print what's at top first and then go to your children. So, surprise, surprise, it's going to be the same thing. So, just a little bit of maneuvering. So, if it's null pointer, again, we're done. So, let's go ahead and return. If it's not, we do some work. So, cout root val, and then you're going to call the left and right. Oh, BFS. I called the wrong function. And that should be it. Except I need to call it to test it. So in this case, it should be 10, 5, 15. It's compiling, and now we execute it, and there you are, 10, 5, 15. Easy peasy, right? We just implemented from scratch a node-based tree and did a DFS and BFS. Now, things to know in the future, this was easy to demonstrate because of the nature of the values I inputted. I first put in what would be the root and then the children. Trees that are advanced in their implementation, namely a red-black tree, could take any value in any order in which you insert them and then create what we call a balanced binary search tree. And you can read in CLRS about that balanced binary search tree. But ultimately, what you need to know is that it's a self-balancing tree that enables you to insert any data set into a tree, regardless of how it's sorted or pre-sorted, or not sorted at all, and still come out with a data structure that stores effectively the values in order and keeps the height optimally minimal. So the height is, if I remember right, no, so the height h becomes the function of the algorithmic efficiency. So a search would be log h, where h is height, as opposed to log n, which is the size of the actual data set, which is significantly faster. That's all I got for round 3, and next time I'm going to go down to the graph implementations for BFS and DFS.